Alright, so hello everyone, I'm Sushi Siddharth. I am a PhD student associated with the Systems and Control Group at IIT Bombay. I'm also the TA for this course, WE19. So let's begin by recording the topics discussed in week 7's lectures. Just one second. Let me check. Alright. Okay, so let's recall. So one of the topics that we discussed after controllability in week 7 was observability of state space system. So to conclude about whether a system is observable or not, there were two tests. One of them was the construction of the Kalman matrix, and the other one was by diagonalizing the system. After this, the concept of detectability was discussed. Detectability or partial observability. And finally, a feedback control design known as pole placement method was discussed. So this is the pole placement technique. So there were two techniques discussed. One was the general technique in which you designed gain k such that the eigenvalues of a minus bk were located at the desired positions in the S-plane, or the other one was the Ackermann's technique. Alright, so let's discuss the first topic. Okay, so just recall the Kalman's test. So let me just, yeah. So let's say you have a system x dot equals ax plus bu. We have n states. So the observability matrix, let's write it as O is given as C CA square up to CAN minus 1. So the system x dot equals ax plus bu, or the pair CA is observable if and only if the rank of this matrix is exactly equal to the number of states. Okay, so let's start with some examples. Question 1. So you have this system, it's a second order system. Minus 2, 1, 1 minus 2. B is 1, 0, and C is 1 minus 1. So note that this matrix does not play a role in determining stability of the state space model. Sorry, observability of the state space model. Okay, so let's form the matrix then. So n is 2. So the observability matrix is C and CA. Alright, so let's compute CA then. and this is given by minus 2 minus 1, 1 and plus 2. So we have minus 3 plus 3, and this implies that the observability matrix is 1 minus 1 minus 3 and 3. So to check the rank of this matrix is a square matrix. So we can simply calculate the determinant, and this is 3 minus 3. So this implies that the rank of the observability matrix is not equal to 2. Hence, this system is not observable. Hence, the pair CA or the system is not observable. Alright. So this was just a second order system. Let's look at the next part. We now have a third order system defined by these matrices. 1 and 0, minus 2, minus 3. So there is one thing that we can observe, that this is in the controllable canonical form. Alright, so now let's form the observability matrix. So we have n equals 2. So observability matrix would be C, CA and CA square. Alright, so let's see. CA is going to be 10, 0, 0 times 0, 1, 0, 0, 0, 1, 0, minus 2, minus 3. So this is 0, 10 and 0. And CA square is simply, so this is 0, 10, 0 times the A matrix again. So this multiplication means that we are extracting this row and multiplying it by 10, right? So this is 0, 0 and 10. Okay, so the observability matrix is 10, 0, 0, 0, 10, 0, 0, 0, 10. So you can observe that this is simply 10 times the identity matrix. So then what's the determinant of such a matrix? So then see, this is simply 10. So therefore this third order system is observable. Right. So I hope this test, the application of this test was clear to you. Now let's move on to the next question. So consider the system. Defined by, so it's a third order system. C 0, 1, 0. So the A matrix is in controllable canonical form. And we have x1, x2, x3 plus 0, 0, 1 times u. And the output is given by C1, C2, C3 times x1, x2, x3. So I'm going to write down what the question is. So accept the trivial choice of these three coefficients being 0. find an example of a set. So let's say C1, C2 and C3 that will make the system unobservable. Alright. So for this we need to construct the observability matrix and then design the values or choose the values of C1, C2 and C3 so that the rank of the observability matrix is not 3. Okay, so let's find those values of C1, C2 and C3. So N is 3. The observability matrix becomes C, Ca and Ca squared. Okay, so let's compute Ca first. So this was in CCF. We have minus 6, minus 11, minus 6. So Ca is simply, uh, first one is minus 6 C3. Then we have C1 minus 11 C3 and C2 minus 6 C3. So let's check this again. This is C11 minus 11 C3 and then C2 minus 6. Alright. Similarly, we have Ca square. So this is nothing but the matrix just computed or the vector times the A matrix. Okay. So this is 36 C3. Then we have minus 6 C3 minus 11 times C1 minus 11 C3 and sorry, that's the last element actually. So minus 6 C3 minus 11 times C2 minus 6 C3 and then we have C1 minus 11 C3 minus 6 times C2 minus 6. So let's simplify this before substituting it in the observability matrix. So we have 36 C3 and then we have 11 C2 plus 66 C3. We have C1 minus 11 C3. We have minus 6 C2 plus 36 C3. This is 36 C3 we have minus 11 C2 plus 60 C3. Okay, and then we have C1 minus 6 C2 and we have 36 minus 11. So this is 5 and plus 25 C. So let's check this before we move on. Okay. So let's substitute this in the observability matrix. We have C, which was C1, C2, and C3. Then we have CA. Let's write this. and then the last row is going to be 36C3 minus 11C2 plus 60C3, C1 minus 6C2 plus 25C3. Alright, so the determinant of the observability matrix is C1 times, so we have this large expression, then we have let's minus C2 minus 6C3 and then we have minus C2 minus 6C3 into C1 minus 6C2 plus 25C3 minus 36C3 C2 times minus 6C3 plus C3 times and we have minus 36C3 times C1 minus 11C3. Alright, so the objective is to choose the values of the coefficients, scalars C1, C2 and C3 such that this determinant is 0. So what we can do is, let's say that let us consider some C1 equals 1 and C2 equals, for example, 0. Okay, so the objective is to find out what is C3. So we have first one becomes 1 minus 11C3, 1 minus 1 plus 25C3, then we have 60C3 plus C3 minus 6C3 to 60C3 minus 36C3 times 1 minus 11C3. So this should be equal to 0. So there's a quadratic equation in C3 which you can solve. So solve this to find C3. So we just need to find one example of this set C1, C2 and C3 that will make the system unobservable. So that is how we can find it out. Or there is one other alternative to this approach. It is that what we can do is diagonalize the system, and after diagonalizing we will have some C bar, and then the condition would be that none of the elements of the C bar should be 0. So that would give us a condition on C1, C2 and C3, and from there we can comment on the values of these three coefficients such that the system is unobservable. So choose C1, C2 and C3 such that the elements of or the components of C tilde are non-zero. Okay, so if this is clear, we have this other topic which we were just discussing about, that is observability of state variable model in Jordan canonical form. Alright, so let's recall the theorem. So we have the system x dot equals ax plus bu, and for observability we also need the measurement, so we have cx plus d. So the system is observable. So if and only if none of the elements of the row matrix C, so this is the case for single output. So if none of the elements of the row matrix C is 0, so C is something of the sort C1, C2 up to, let's say, Cn. Yeah. So C1 should be non-zero, and all of the coefficients should be non-zero for the system to be completely observable. This is the case when there is just one input. So for multivariable case or multivariable systems, so let me write down the C matrix for that. So for example, we have C11, C12 up to C1n, and let's say that there were some Q measurements. So this is C21, C22 up to C2n. This goes on till CQ1, CQ2, all up to CQn. So this is a Q by N matrix, where Q is the number of measurements or outputs. Alright, so when is such a system observable then? So we are assuming here, of course, that the system was diagonalized first. So the matrix, uh, just this is a note that the system x dot equals ax plus bu, y equals cx plus du has already been diagonalized. So this means that the A matrix here is the diagonal matrix, right? For distinct eigenvalues, we have up till e to the power lambda nt and zeros here. So this is the system we are talking about. And this is C, or what we consider in our lectures is C tilde. Okay. So this is the theorem that the above or the diagonalized system is observable. So it's an if and only if condition. If none of the columns of the matrix C or C matrix is a zero column. So this is because let's say that Y was just simply Cx and this is C11 up to C1n or up to CQ1 CQn times x1 through xn. So this is actually a q by 1 vector. So when are all the states observable? So you can write this right hand side like this, right? X1 times the first row, C11 up to CQ1 or up to xn times the last row. So this is a linear combination of the columns of the C matrix. So if any of these columns are 0, then this term vanishes from the measurement and we say that that particular state is not observable. So that's why the theorem states that the system is observable if and only if none of the columns of the C matrix is a zero column. So let's look at some cases now. I think this is 3. Okay, so we have the first system. So I will be writing down the system after it has been diagonalized and we just have to comment on whether the system is observable or not. So let's see. We have x1 dot x2 dot equals -1 0 0 minus 2 x1 x2. So we don't need the input right now. So let's talk about the measurement then. It's 1 3 times x1 x2. So for a single output case, we just have to check whether the elements of the C matrix are 0 or not. And we can observe that these are not 0. So the system is observable. Alright, so now let's look at a third order system. Again, it has already been diagonalized. So let's see. 2 1 0 0 2 1 0 0 2 times x1 x2 x3 and then we have y1 y2 3 4 0 0 0 0 x1 4 x2 and x3. Okay, so observe that we have 3 repeated eigenvalues at located at lambda equals -2, sorry, +2. Okay, and we have 2 outputs. So we need to observe the first column, and if this is non-zero, then we can comment that the system is observable. So in the case of repeated eigenvalues, we look at the first column of that corresponding state in the C matrix. So the conclusion is that the system is observable. Okay, so this was just the case when we had 3 repeated eigenvalues. Let's see if we have some more eigenvalues for a higher order system. We have a fifth order system, x5 dot. So again, there are three repeated eigenvalues at 2. So we have a Jordan block 2, 1, 0. Then it shifts 0 to 1 and then 0, 0, 2. Then we have two repeated eigenvalues at -3. So that would look like -3, 1, 0, -3. So we have this matrix. All elements are 0 here and 0 here. Okay. Then we have x1, x2, x3, x4, and x5. And now we need to talk about the measurement. So we have two outputs available to us. So let's write them down. 1, 0, 1, 1, 1, 1, 0, 0, and 0, 0. We have x1, x2, x3, x4, and x5. Okay, so now let's look at this first column. This is for lambda equals 2, and we have this one for lambda equals -3. So you can observe that these two states never appear as the output, so the system is not observable. Sorry, so I'm going to rewrite this again. Sorry about this. 1, 0, and then if this is 0, 1, let me write this down. This is for lambda equals -3. In this case, the first column of the repeated eigenvalues are non-zero, so we can conclude that the system is indeed observable. Okay. Okay, so we have concluded when the system is observable or not based on the diagonalized system. And there are two separate theorems for the case of single input and for the case of single output, and for the case of multiple outputs for the system. Okay. So now let's move on to the next question. So we have again a third order system. So it's -1, 0, 0, 0, -2, 0, 0, 0, -3. So the system has distinct eigenvalues, and we also have some input 2, 0, 0, 1 times u, and then we have the output y, which is 0, 1, 2, 0, 1, 0. Okay, so this is a multi-output system, and the question is, what can we say about observability without making any further calculations? Okay, so observe that this system has distinct eigenvalues at lambda equals -1, -2, -3. So this implies that the system is already diagonalized, right? Or it is already in the diagonal form. So the C matrix is 0, 0, 1, 1, 2, 0. So according to the theorem, for distinct eigenvalues, none of the columns should be 0. So this state associated with lambda equals minus 1 is not observable. So this implies that the system is unobservable. Alright. So I hope this was clear to you. Now let's talk about detectability of the system. Detectability or partial observability. Alright. So the definition for detectability is as follows. So for a partially observable system, if the unobservable modes are stable and the observable modes are unstable, then the system is said to be detectable. So also note that the concept of duality was discussed in the class. So if a pair AB is controllable, then we have a corresponding system associated with the matrices A and C, which is observable, right? So according to the principle of duality, we have a relation between detectability and stabilizability. So I'm going to write that down. So note that the concept of detectability is dual to the concept of stabilizability. So this talks about partial observability, and we're saying that this is dual to the concept of partial controllability. So just a note about the principle of duality. So for the controllability matrix, so let's write this down as some C. We have B, AB up to a to the power n minus 1b. So controllability implies that rank of C is n. And observability, which is C, CA or up to CAN minus 1. The rank of this matrix is n. So let's say that this is for the system S1. S1. That is x dot equals ax plus bu and y equals cx plus, let's say d was 0 here. And now let's define another system S2. So for that case, the controllability matrix is formed by the A and B matrices for the system C2, which are related to the C and A matrices of S1. So I'm going to write this down as C transpose, A transpose, C transpose, all of it, A transpose N minus 1 and C transpose. Let's say this was for the system S2. Observability matrix for S2 becomes B, A, B, and A to the power minus 1. So if this is the case for the system S2, so the rank of C prime is n for controllability, and rank of those observability matrices n. So then what are the matrices associated with S2? So we have A here is A transpose, which is obtained from here. Then we have C transpose instead of B, and then we have B. So the system S2 is dual of the system S1. So if you have to talk about controllability of the system S1 by using this matrix, we can also comment on the controllability by defining this matrix C prime. So then how do you check observability of the original system? By checking controllability of C prime, right? So if the rank of C prime is n, so rank of C prime is n, and we know that C prime is actually the transpose of the observability matrix, original matrix, and the rank remains the same after the operation of transpose. So if you have to talk about observability of the system S1, we talk about controllability of the dual system, which is S2. Okay. So let's look at some examples of detectability. So I'm going to write down the systems which are already in the diagonal form. So let's see. We have the first system x1 dot x2 dot equals -1 0 and 0 minus 2. X1 x2 and y is 0 1 x1 x2. Okay, so the system is already diagonalized. Is the system partially observable? Yes, right? You can see that the system is not observable because one of the elements of C is 0, and this corresponds to lambda equals -1. So the stable mode is unobservable, but here the one of the other stable modes is also observable. So our conclusion is that the system is uh, this is not completely observable. Alright, so let's look at a third order system now. We have already looked at this in the previous question. We have 3 repeated eigenvalues at 2. So the Jordan normal block will look like 2 1 0. Then we shift this 0 to 1, and then again 0 0 2 times x, and y is given to be. So we have two outputs. We have 0 0 1 2 3 4. So you can see that the first column is 0. So hence the system is not completely observable. Because in the case of repeated eigenvalues, we focus on the first column associated with the eigenvalue. The system is not completely observable. You can also find out the rank of the observability matrix, and you'll find out that this is not equal to 3 for n. So next we have a fifth order system. composed using this third order system. So we have x1 dot up till x5 dot. Okay, so 3 repeated eigenvalues are 2. So this is the Jordan block. 2 repeated eigenvalues at -3. So this is the Jordan block. And then zeros everywhere else. Times x and y looks like. So we have two outputs. 1 0, 1 1, then 1 1 0 0 and 0 0. So there were 5 states: x1, x2, x3, x4 and x5. So for repeated eigenvalues, we look at the first columns. So this and this. So this is fine. This is non-zero column, but this is 0. So hence the system is not completely observable. So in the case of repeated eigenvalues, you need to look at the first column and then comment on whether the system is observable or not. Alright. So if this is clear, let's see what the next topic was. It was the pole placement technique. Yeah. Okay, so let's recall a few points. Okay, so we have the general state space model x dot equals ax plus bu, and let's say that all of the states were measured. So we have a completely observable system. So let's say that if we assume that all the n state variables x1 through xn can be accurately measured, at all times. That is, we can construct a feedback control law using these measurements. So accurately measured at all times. Then it is possible to implement a linear control. So linear in the state. So implement a linear control which looks like this. So you have the control view minus k1 x1 minus k2 x2 all of it minus k3 xn. So this can be written as this row vector times the state. So you have this matrix minus k times x. So k is a row vector of size n by 1. Okay, so k's are scalars or real numbers. And if we implement this u in the state space model, so we get x dot equals Ax plus b times minus kx, which is nothing but a minus bkx. Okay, and then the characteristic equation. So this is now known as the closed loop model, closed loop system, because we have taken feedback from the using the measurements and supplied it back to the plant. Okay, so the characteristic equation of the closed loop system is say the determinant of a minus bk minus lambda I should be equal to 0. So you get an nth order polynomial from there. So that would be the characteristic equation. Okay. So let's say that the desired eigenvalues, so we know their locations already. So the desired eigenvalues, let's say located at uh, S or lambda, we are talking about this range. So at lambda 1, lambda 2, and so on to lambda n, where all of these lambda i's can be real or complex. Real, or if they are complex, they should occur in pairs, right? Or complex conjugate pairs. Okay, so you know these n eigenvalues, then you can form a polynomial such that the roots of that polynomials are exactly these eigenvalues, right? So how do you form that? That is s minus lambda 1, s minus lambda 2, all up to s minus lambda n equals to 0, gives you a desired characteristic equation. So you can expand this and you get an nth order equation from here. Let's say this was 2, and you get an nth order equation from here in terms of the gains k1, k2, and so on, right? K1, K2 up to Kn. And then you can compute the similar parts of both of these polynomials and get the values of these gains. Okay, so let's look at a question. This is just 1 second. Okay, so this was the fifth question. Alright, so let's say that we have the following state space model. X dot equals 0, 1, 0, 0, x plus 0, 1 times u. So the eigenvalues of A can be computed by A minus lambda I determinant. This is minus lambda 1, 0, minus lambda. There is lambda square minus 1. So right now we have the eigenvalues at 1. Okay, so let's say that to place these eigenvalues at some desired location, we have this feedback control law minus k1 x1 minus k2 x2. Okay, this is some vector times x, and then the closed loop system becomes this is a minus bk times x, right? So let's substitute these matrices. So we have 0, 1, 0, 0, minus b times the gain matrix K, that is K1, K2. This times the vector x. So x dot is equal to 0, 1, 0, 0 minus K1, K2. Now this is 0, 1 minus K1 minus K2 times x. So then what's the characteristic equation of the closed loop system? So let's say this is the closed loop matrix A. So ACL. So ACL minus lambda I. The determinant of this is, let's say, minus lambda 1 minus K1. This should be equal to 0. Alright, so let's expand this now. Minus lambda minus K2 minus lambda, then plus K1 equals 0. This implies lambda square plus K2 lambda plus K1 equals 0. Okay, so we have this equation in terms of the gains. And let's say, so this is a second order system, right? So the design specification is, sorry about this. That for the second order system, you want omega n to be, okay, let's say not omega n, the damping ratio psi to be 0.707 with a settling time Ts of 4. Okay, so the formula for settling time is 4 upon psi omega n. So we have um, omega n becomes 1 by psi, right? Yeah, okay. So if this is the case, then what's the desired characteristic equation? It's simply s square plus 2 zeta omega n plus omega n squared, right? So this is the desired characteristic equation. So let's compute this first. S square, or in terms of lambda, that's fine. S square plus 2 zeta into 1 upon zeta plus 1 by zeta square. So this is 1.737 square. Okay. So if you solve this equation, you get that the desired eigenvalues are, let's say this, that the location of the desired eigenvalues are lambda 1 should be equal to minus 4 plus j4, and the other one is minus 4 minus 2. So these are occurring complex conjugate pairs, and we have the characteristic equation as s square plus, sorry, this should have been s. Yeah. Alright, so sorry about this. Let's say that the desired specification is that we want the poles to lie on these locations. Lambda 1 equals minus 4, or just 2 lambdas. So then the characteristic equation is simply s plus 4 minus j4 times s plus 4 plus j equals to 0. So let's expand this. The first one is s square plus 4s plus 4s and 4s plus, and then the last ones are going to be, sorry, 16. This should be 0. So let's see if something cancels out. We have plus j16 minus j16, and then you have this order. So the desired characteristic equation is plus 8s plus 16. So let's name this as, number this as 2. And now let's see. So we have equations 1 and 2. So this is the desired characteristic equation. And now to find the values of the gains, we just need to equate the coefficients of similar parts, right? So K2 should be equal to 8 and K1 should be equal to 16. This is by comparing equations 1 and 2. Okay. So if this is the case, you can also check if the eigenvalues are exactly at the desired locations. You can just check this by substituting K1, K2 in A minus Bk and then computing the eigenvalues. So just check this at the end if the computations are correct or not. Alright. So this was the case when we have just used the brute force method. We have some A matrix. We have computed A minus Bk and then equated the two equations. So the alternative approach is to first convert the system into the CCF form and then design the game, right? So recall that. So let's say that you have some given system x dot equals ax plus bu, and A is not in the CCF, or the whole system is not in the controllable variable. So for example, we have some new variables x bar, which is related to x by this transformation p of x, such that the system dynamics or x bar dot is in the CCF. So let's say that this P matrix is invertible. It's a square matrix n Pn1 through Pnn. Then we have x1 through xn, and so you have this transformation. So the new matrix A bar is going to be PA P inverse. So let's say that this A bar is in the CCF form. So this should be 0 1 0 0 0 1. The last row should be, and then some coefficients, right? So let's say minus alpha n minus 1 minus alpha 1. Similarly, we have some B bar, which is P times B. This becomes 0 zeros and 1 at the end. Similarly, we have C bar. Okay. So then what's the characteristic equation for this transform system? It's simply Si minus A, the determinant of this, right? Si minus A bar. Okay, so this is simply Sn plus alpha 1 times Sn minus 1 up to alpha n minus 1 S plus alpha 1. Alpha n. Okay, so we have this characteristic equation of the transform system. So x1 bar is going to be some E11 x1 all up to So these are the elements of the first row of P1, sorry P. So this is P1 times Xn. So X1 dot would be P11 X1 dot up to P1n Xn dot. Okay. So I think you can recall from the lecture series that this new variable x is related to some p times x, and by following this procedure you get the rows of the p matrix, right? So the first one is p1, then you have actually first row times a, and then all up to p1 to the power n minus 1 times x. Correct. Similarly, you have for the new transform system b bar, which is pb. This should be 0, 0 and 1 throughout, and this is actually P1B, P1 times AB, P1 times A square B, all up to P1 times A to the power minus 1. Okay, and how do you find this first row of P? So P1 is actually 0, zeros and 1 throughout times the inverse of the controllability matrix. You can see from here, right? So if you equate these two, and you can find P1 by inverting the controllability matrix. So you can only find this control law if you have a completely controllable system, because you need the inverse of the matrix. Alright. If you have this P1, then you have the states x bar. Then the control U is going to be minus k of x bar, where this, let's say, okay, sorry, k bar. And in the original dynamics, we have minus kx. So the relation between k bar and k is the multiplication by t inverse. So or k is equal to 3 times k bar. So you design this, design the controller for the controllable canonical form, and then you use the transformation to get the controller for the original system. Okay. So let's look at an example. So I'm going to directly write down the A and B matrices. So 0, 1, 0, 0, fourth order system. We have zeros. Similarly, we have B. So this is 0, minus 1.4458, 0 and 0.9639. Okay. So then what's the characteristic polynomial for this system? It's simply Si minus A determinant equals 0. Right? So you can compute this. I'm going to write this down directly. 16 3.106 S square equals 0. So you have two roots at the origin, and then you have a pair of complex conjugate roots. What is it? Let's see. So you have S equals 0, 0, and okay. So this is okay, 4.039 and minus 4.039. So we have four roots where these two are repeated at the origin. Okay. And then we also have one positive root which will lead to instability. So we need to place the poles at some desired locations or in somewhere in the left half of the S-plane. So let's see. For that we need the controller U minus kx, which is linear in the gains, right? Minus kn xn. So linear in the states. Alright, so let's say that we want to place all of these poles at some location s equals minus 1. So we have 4 poles at -1. Okay. So we'll find out this controller u equals minus kx by the method we have just described. So the controllability matrix is, it's a C. This is a fourth order system. So B, AB, A square B, and A cube B. Alright, so you can conclude this and write this down directly. 0 minus 1.4458. Then the next is and then 23.5816, 0 and 1.5379. Then we have zeros again 1.5379, okay, and then 0. So this is the controllability matrix. So you can check that the system is controllable by finding out the determinant. So rank of C is 4. So you can find out C inverse now. So you have some matrix 0, 0.0750, then we have 0, 1.15, okay. So if this is the case, then what's the first row of the transformation P? So it is simply here, right? So P1 is the last row of C inverse. So P1 is simply 0.0470, 0 minus 0.075 and 0. So now that you know the first row, you can always find the whole transformation matrix, right? So that is given by P equals P1A. So just P1. Then the next is P1A. Then P1A square up to. Okay, so the last one is P1A cube. So you can substitute these and find out that this is some 4 by 4 transformation matrix. Alright. So this is minus 0.0470, 0, then minus 0.6917, okay. So you can check this on your own after the class. Okay. So then the characteristic equation, we already have that. So now that we know P, just let's see how we can find K then. Okay. So we have the controllable canonical form. So Si minus A is, we have a characteristic equation. Then we also have the characteristic equation for Si minus A minus Bk, right? In terms of the gain K. So let's see. We want this to be equal to s plus 1 to the power 4, right? Because we want 4 poles at minus 1. So what we can do is expand this determinant, and this would be a variable of k1, k2, k3, and k4. So then we already have A and B in the CCF form. You can substitute A and B from here. Plug those in Si minus, this would be Si minus A plus Bk. and the equation would be in terms of k1 through k4, and then we just need to compare them with the coefficients of s plus 1 to the power. So let's say we get some k here. Let's say that was k bar because we are computing this in the CCF form. And so we got some k1, k2, k3 and k4. We are not done yet because we want to design the controller for the original system. So for the original system we have, let's go to the above transformation, we have p times k. Let me just p times k. So we have already computed this using this. We already know what k bar should be, and so we know that what is k. So the original control law is u times u equals k minus u equals minus x. So another approach which uses the Cayley-Hamilton theorem is the Ackermann's technique. Ackermann's formula. So according to this, recall that the gain vector or the gain matrix K is given by this times the controllability matrix inverse times the characteristic polynomial formed using the Cayley-Hamilton technique. So let's look at the question. Okay, so let's say that we have a simple second order system 0 1 0 0 plus b times b. Okay, so let's say that the desired characteristic equation so we have some desired location of the poles. From there we have this equation s square plus 8s plus 32 equals 0. Okay. So to find the gain matrix K, we need to find the controllability matrix first. So let's form this. The simple second order system we have B and AB. Okay, so AB is 0 1 0 0 times 0 1. This is simply 1 0. Then C becomes 0 1 and 0. So the determinant is minus 1, right? So this pair is controllable. We can find the inverse, and the inverse is simply 1 upon determinant of A. You interchange these and change their sign. So 0 1 and 0 1. Okay. So we know what C inverse is. Now we need to find the characteristic polynomial. Alright. So the characteristic polynomial is xi minus a minus determinant. So let's see. We have s, then minus 1, s0 and s. So this is simply is it simply s square, then let me check. Yeah, s square. So right now the poles are at 0 0. And we want the codes to be here, right? Lambda 1D and lambda 2D, which are the roots of this polynomial. Okay. So the characteristic polynomial by the Cayley-Hamilton theorem is given by. So let's start with the lowest power of A. We have alpha 2 times A plus alpha 1 times A plus A square. So we already have the matrix A. After substituting this, we get 1 0 0 1 plus alpha 1 times 0 1 0 0 plus A square. So let me just see this. A square is 0 1 0 0 times. So the first one is 0, and then we have 0. Okay. So we can negate this term or just write 0 1. So this is alpha 1 times 0 1 0 0 plus alpha 2 times 1 0 0 1. So we equate this with A square plus 8 times the matrix A plus 32 times I, right? Because this was the desired characteristic equation. Okay, so then we have this is 0 plus 0 8 0 0 plus the identity matrix, right? 32 0 0 32. So we have component wise addition, so 32 8 0 and 32. So this is phi of A. And now we can just substitute these two in the formula to obtain the gain matrix. So this is simply 0 1, like a second order system. Then we have the inverse of the controllability matrix 0 1 1 0, and finally phi of A. So you can conclude this. This is just the last row 1 0. Okay, okay, so we can also check if we apply u equals minus kx in the original system. So this is just for checking purposes. Check whether you have computed the gain matrix correctly. So this is simply 0 1 0 0 minus 32 8 b times 32. Let's say 0 1 0 0 Okay, so what's the characteristic equation then? This is in CCF, right? So the characteristic equation is simply lambda 0 0 lambda minus 0 1 minus 32 8 and its determinant. So let's expand this. Lambda square minus 8 lambda plus 32. Okay. Okay, so I think there's a sign change somewhere. We started with this plus 8s, so let's see. Um, okay, so this, yeah. So I think there was a sign mistake somewhere. Uh, Lambda minus and minus. This is plus. So lambda square plus 8 lambda. So this was exactly equal to the desired characteristic equation so that we started with. So if the computations are long or if you have a higher order system, then I would suggest that you always check at the last whether you got the same desired characteristic equation or not. So that's it for today. If you have any doubts regarding the quiz, you can ask me. Yeah, sure, you can use the Ackerman's formula if that's easier for you. It's fine. Is there a question in the quiz in which it's not mentioned? Let me check. Oh, okay. Yeah, in that case, you just have to use Ackerman, but you are free to use either Ackerman or that general pole placement technique as well. It's fine. Yeah. Okay, so if there are no more questions, let's stop for today.